Yeah.
Okay. Can you hear me? Can you now hear me?
Yes, much better. Okay, so our first speaker of the last day, congratulations for making it after the dinner, is Esteban Castro, who will tell us about reference frames and quantum reference frames, which is maybe a more concrete approach than what we've been seeing so far. We've looked at things very formal, and now we're going to talk about more concrete systems, which is exciting.
Okay, so hi, welcome to this introductory course on quantum reference frames. So let me briefly tell you what I will talk about, so kind of an overview. So quantum reference frames is a very broad topic that exists for a long time, and I will not be covering all of it, of course. I will cover a subset of this broad topic, which could be called quantum reference frame transformations. So we will talk about symmetries in quantum mechanics and try to define broadly a notion of what it means to jump into the reference frame of a quantum mechanical system. Kind of the motivating question of all this recent research line is that one, and to make a precise sense of such a question is kind of the goal. There's many recent works on that question or related questions. I will not cover, of course, all of them, although I wrote a list of references. This list is non-exhaustive, but you can look it up, and I will make reference to the reference as I go along. Sometimes just by number, and then you just look up the number, or sometimes I will just mention the authors or the title, etc. So you have some notes for the course, the things that I planned to talk about. It's likely that I will cover also a subset of those, depending on the pace. Please ask questions, and I'll go as slow as I can, as detailed as I can. So quantum reference frames, or reference frames in physics, are a very important notion, of course. Like, they're everywhere. If you write down something like this, for example, this is something you see in your first course of quantum mechanics, right? It's the position basis expansion of a quantum state, right? Already here you can see that there is an implicit reference frame here, because what is this x? What does it mean that I expand my wave function in terms of x? This x is obviously defined with respect to a reference frame that allows me to measure the position of the particle, or to determine what is the position that I will later explore and see if I find the particle there. So more concretely, I'm thinking of something like this. No. So how do we make sense of this x in practice? Like, in the laboratory, we put something, let's say this piece of chalk or this corner of the table, and then with a piece of tape, we measure a certain amount of centimeters, millimeters, etc., and we determine what this x would be. Let's say it's here. And then the meaning of this x in this equation, or in this state, is just the square of the wave function equals the probability that I find the particle around this point x. But I had to fix, of course, a reference frame first. Given a reference frame, which I call A, I can make sense operationally out of these things, right? This is very basic. I just want to highlight how basic and important it is. And it's important to note that even though mathematically we can choose coordinates and express this in an abstract way, whenever we go to the lab, what we really do is we put a table or a piece of chalk or something material, right? And then an important question in physics, like everywhere, is what happens if we have another reference frame and we want to describe the same physical situation. physics should not depend on the reference frame that I'm using to describe it, right? This is called the principle of covariance. And because of this principle, it's very important that our equations or that our laws have transformation rules that highlight this principle, that make sure that the physics does not depend on who is looking. So if I have another reference frame, say B, then B should also be able to describe the system. Let me use another color for the system. Let's say this wave function is something like this, right? So this is S, this is A, and this is B, right? And let's say that B is displaced by alpha with respect to A, so that the origin of B is at a distance alpha from the origin of A. And then we can ask the question, how would B describe such a state? And how do we make sure that everything transforms in the correct way? There's two ways to do this, of course. You can do either an active or a passive transformation. You can leave the state as it is and change the basis, right? And rename this basis as the natural basis that B would choose to describe physics. Or you can also actually take this wave function and move it, right? Actively. And then when it's moved, it would be as if we would be in a situation in which Bob is at the origin instead of Alice. So more concretely in this case, we're talking about position basis. We're talking about translations. B's reference frame is translated with respect to A. Then the state, as seen by B, I will be writing these things a lot. So the superscript under parentheses means the perspective that I'm taking. I will sometimes write this or sometimes write also this. S is the system that I'm looking at, and B is the one who is looking at the system. This is just notation. I will use sometimes this one, sometimes this one, so that you know. Okay, so I guess you would all agree with this. Let me put maybe here, so as to make sure that this is just saying the wave function as seen by B is just the wave function as seen by A, but displaced. Why is it plus and not minus? It's actually the wave function, this function that needs to be shifted like that towards the back, but this changes with the opposite sign as the ket vectors, right? So if I put a minus here, I should put a plus here, and this is what I'm doing here. Okay? So all of this is, of course, very basic. And now comes the question. If I am saying that this B, that this A and B are by necessity physical systems, stuff that I put in the lab, then they are also quantum systems. They are also subjected to the rules of quantum mechanics, if we believe that quantum mechanics doesn't break up at some point, which I think it's a very reasonable thing to believe, given experimental evidence. Then it makes sense to ask, what would it mean? Can we extend our notion of symmetries? This is a notion of a symmetry transformation. It's a transformation between reference frames. Does it make sense to ask, can we jump to a reference frame which is quantum mechanical, which is in a superposition between, say, different locations, instead of being sharply localized at alpha, for example? So this is, I think, an interesting question that touches upon many important aspects in quantum physics. And the goal of these lectures is to make a proposal for such a thing. These are very recent works. It's a very recent research field. There's many open questions. I will try to answer your questions the best I can. But you will see that immediately there's so many very interesting things going on. So I will now motivate how to jump into a reference frame or propose a mechanism, a formalism, by which we can make sense on how to jump to a reference frame.
Is there any reason you tilde on the left side?
Just to say that this is not necessarily the same wave function, right?
So it's not enough to change the reference frame. You also have to...
Yes, yes. So this, for example, tells me who is looking, but then this tells me what the function is, right? Which is not necessarily the same function. So this label does not mean that this whole thing is a different thing. If I would put the same psi here, it's just notation. It would mean that B is looking at exactly the same function as A, but this is not necessarily true. So this is why the tilde appears. Like, yeah. In this example, you would have this. Right? This is how the two are related. Okay, good. So, but first I would like to motivate why would we do such a thing, or why are we interested in jumping to quantum reference frames that are in a superposition of locations, for example. And it turns out that there's some situations in physics in which the normal transformations that we're used to, in which the reference frame is a classical thing, like an object that is sharply localized at a certain position, for example, are not enough. Or if they're not enough, there's certainly some clarity to be obtained from allowing a more general type of transformations. One example is the case of spin in special relativity. So how do we define the spin of a particle in special relativity? If you open a textbook, you will read that the spin of a particle in special relativity is defined as the total angular momentum in the rest frame of the particle. This makes a lot of sense. Like angular momentum is the orbital part plus the spin, right? If we jump to the reference frame in which the particle is at rest, this goes away. So the remaining part is this one, and then we're happy because the spin is really the total angular momentum in that frame. And then if we have a particle that is moving with a certain velocity, all we have to do is to jump into the reference frame in which the velocity or the momentum, more precisely, is 0. And once we do that, we reach the good reference frame in which I can operationally define the spin. If I were in that reference frame, I could put some Stern-Gerlach magnets, do the experiment, and all the results would be as in non-relativistic quantum mechanics. So I could treat the spin as a qubit, so to speak, which is, of course, very useful if one wants to do quantum information and so on. But there's a problem here, right? Can any of you tell me what the problem is?
You need to know the momentum of the particle to go to the rest frame.
Yes, more or less. It's not that you need to know it a priori. It's even worse, right? It's not that there is some momentum and you don't know it, and then somebody has to tell you, and then you are happy. It's more, there are quantum mechanical states in which the momentum is not defined, right? You could write something like, for example, this, which would be the case of a particle propagating along two different directions. And then you tell me what is the reference frame in which the particle is at rest, right? How do I define spin in such a situation? So you can do it if you enlarge the set of reference frame transformations that you want to consider. If you would like to put, for example, another quantum system that follows the particle, so to speak, can also be in a superposition of different momenta, then you can jump to that reference frame. Like this. And then if you do it, you will find that the particle is at rest in that reference frame. And then you can do a Stern-Gerlach experiment and so on. Of course, this is all very, it's not clear how technologically one would do that, of course. But at least one could mathematically analyze the situation as if we would be able to perform such a change and then change back to the laboratory coordinates. And we will know, depending on the measurement that we want to do, how to orient our magnets to get the protocol that we want to do, right? Okay. Another example. Let me do here another example, which I think it's perhaps a very interesting potential direction of all these fields, is the physics of quantum systems that gravitate. So imagine you have a relatively heavy piece of material, like I don't know, a lemon or something like that. And then imagine that you can put this lemon in a superposition of two different positions, so that it's like here and here. And then you ask, what is the gravitational field attached to this lemon, or that is sourced by this lemon? And this is a question that is not extremely clear, given our theories of physics, what it means, right? If we would like to understand it intuitively, this doesn't mean you cannot perform calculations and predict answers and so on. It doesn't mean that, but it means that this is a very non-intuitive situation in terms of how fundamental physics is phrased, in which the metric of general relativity is assumed to be a fixed thing, right? If you go and open a book of quantum field theory in curved spacetime, for example, you will see that the metric plays a very, very fundamental role in the way we build the Hilbert space for particles and so on. So once you don't have that, it is at least a kind of new, different situation. But it turns out that one can use quantum reference frames to gain some insight into this type of situations. How? Here is quite obvious, right? You can just jump into the reference frame of the lemon, right? And then if you jump into the reference frame of the lemon, this is of course very approximate. I'm talking about semi-classical states where I'm neglecting the fact that this lemon also kind of has an intrinsic uncertainty, each of these states of position and momentum, right? But given this approximation, I can jump, and given this approximation, I can say that the field, the, say, Newton field attached to the lemon is now well defined. And then I can answer questions such as, for example, if I could ask, how does a particle move here? Well, it's not in principle completely obvious what I will do. Some strategy would be to jump into the reference frame, and then the particle might start in a superposition, for example, or be in some weird state. But nevertheless, this is a completely standard situation in quantum mechanics that we can figure out how to compute things and how to work with it. And then we can jump back and see the consequences. Okay, so this is more or less, I gave you a couple of examples in which I think quantum reference frame transformations can give interesting insights in physics, in certain problems in physics, in which our usual notions of reference frames are not enough. Now what I will do is I will try to propose a way to jump into a quantum reference frame. I don't know what's better. Should I not erase and then maybe, huh? No, wait. I will use that. I will erase. Okay, something happened. Okay, better. Yes?
In principle, try to put the one you already written on all the way up.
Oh, sometimes there's other buttons and there's something sitting on top of other buttons.
Okay, let me then erase this thing. What happened? Are there any questions so far? In the meantime. Oh, thanks, Lydia. Oh.
It's my classmate to the break. Do you really want to erase?
Okay, no, let's try not to. Good. Yes. Okay. Thank you. Yes, so let's start with that picture again, and let's start with that equation again, and let's try to generalize it. So what's the idea? The idea is we want to treat the reference frame as a quantum system. So what do we need to do? Obviously, we need a Hilbert space for that quantum system. So before, we have, say, A, in that case, and B, and then we had a system, and the game was, how does A observe the system, and given a state that A observes and attaches to the system, what is the state of the system relative to B? Given that information, how do we compute the other one, right? Now the situation is going to be slightly different, right? Because we would like to quantize the reference frame. So if we want to quantize the reference frame, the situation will be as follows. We have A, and we have B, and S, but now A describes, of course, not only S, but also B, because B has to have a Hilbert space and has to be a physical system which is observed by A. And then the game is, given a description of B and S as seen by A, what is the description of A and S as seen by B, right? And then I'm going to make small modifications to that equation as to reach the quantum reference frame transformation that I want. So let's say first of all, I will start putting sub-indices here of the systems that I'm observing. And then I will say that this is this operator acting on S. And then if we look at the picture, starting from A, where is B? Well, at alpha. So I will put B at alpha, right? And then I will put whatever system I have, whatever state I have into the system, right? But here already there is a problem, which is that the labels will not match, right? So I will have to do something about the labels. As I said, I start with a situation in which A describes B and S, but I want to end up in a situation in which B describes A and S. So if we were in this picture to keep the orientation of the x-axis here, then if A would see B at alpha, then it's natural that B would see A at minus alpha. So I'm going to kind of supplement here this by something called the parity swap operator, going from A to B. It's tricky sometimes, the notation, because this is something that acts on B and gives something that lives in A, and it's defined as follows. Right? This is just to capture the fact that if A sees that B is at alpha, B sees A at minus alpha. Okay? And now comes the important point. So this is one change, parity swap, in order to, instead of having, so the usual Hilbert space quantum transformation of reference frames goes from the Hilbert space of the system to the Hilbert space of the system, and it's a unitary map. Now we want to find a map that is unitary as well, but goes from the Hilbert space of B tensor the system to the Hilbert space of A tensor the system. This is roughly speaking. I will be more precise later. Okay? Some questions?
Yeah, I'm just in doubt. In what frame is the psi on the right hand side, top equation?
Here is in A's. Yeah. Okay, now here comes the important point, which is the important trick, which is simply to note that I have alpha here and I have alpha here, right? So this guy is like reading where the reference frame is, and depending on where it is, applies a translation on the system. So I could as well write this as like that, right? Because then when this operator hits this, it becomes alpha, and then it becomes the classical reference frame transformation that we had before, right? Okay, now we're done. Because now, if you look at this expression, it doesn't depend on the initial state of the reference frame at all. It's just an expression that automatically reads the reference frame of B, reads its position, and then translates in a quantum controlled way depending on this position. And then we can interpret this, or we can take this object independently of the specific situation that we started with. We can, let's define it. Let's call it S from A to B is equal to P from A to B, which I define there. So now the parameter of the transformation, which was alpha, becomes an operator. So this is kind of the first example of a quantum reference frame transformation that we have. And the thing nice about it is that it does not depend on where B was in principle. I don't have to come up with a different S depending on the different input states that I have for B. I will just automatically, by quantizing B, read out the states and transform accordingly. Okay? Are there any questions?
Yeah. Are you assuming an on-take interpretation implicitly?
Am I assuming? No, I think what I'm saying is fairly independent of the interpretation you like of quantum mechanics. Yes. Yes. I don't know why you would need an on-tick, but we can talk about it later if you want. Yes. Okay. So is there another?
Just to clarify, the lowest equation is S from B to A, right? The very lowest equation would be S B to A.
Sorry. Yes. This goes like if I want to go from the reference frame of A to the reference frame of B, I would start in B because A sees B, and I will end up in A. Right? Okay. Is this clear?
Yeah.
It's confusing, and I haven't found a happy notation for this, but this is how it is. Okay, now let's do an example of these transformations, because now we're allowed to use some more general states for the reference frame, right? We started by saying, okay, the reference frame of B is classical, it's sharply localized at position alpha, and then by construction we will obtain normal reference frame transformations in the classical case, just by considering specific states for the reference frame B. But of course, the interesting part is to ask, what if B is not in that state? What happens when we apply this transformation where B is in a superposition or something like that, right? And this is what I will do next in a quick example. I just want to check the time. Now I will erase.
Question.
Yes?
What if you have defined P A to B of x3 as minus x, right?
Here.
Yeah. So the definition of the reference frame depends on the fact that there is a P which gives me that, right? But
Yes.
there is a symmetry in the problem where you're not able to distinguish. I mean, where P A to B XB is equal to XB itself, let's say. So then, meaning to say, if there is a symmetry in the problem where you don't have such a scenario, then how do you define your reference frame?
I'm not sure I understood your
For example,
question.
You say that there is a permutation operator, right?
There is a what, sorry?
It looks like a parity operator.
Yes, yes.
So if there is a symmetry in the parity itself, so then how do I define?
You define it like that, and you will find that when you jump to the reference frame, there will be a symmetry. Yeah. It's a particular case of the transformation, but this property will be preserved when you, and it will be a particular property of an instance of a physical system that will be captured independent of how you define this, right? Yeah.
You're assuming that A and B are at this, like systems of the same size, don't you?
Yes, let's. I will talk about this later. I will comment on that later, but or maybe I will comment on it now. Yes. So this is part of the kind of tricky questions here. What I'm assuming, it's I've been presenting this as if they were particles, right? The Hilbert space of a particle and so on. And then I say, oh, a particle sees another Hilbert space, associates another Hilbert space to B and A and so on. So what does it really mean, right? How can a particle associate a Hilbert space? If you're an operationalist, a Hilbert space is defined by a set of laboratory procedures and operations and so on. So what I really mean here is that both A and B, when I say A and B, I don't mean necessarily a fundamental particle or something like that. I mean, let's say, a degree of freedom of let's say, something like a platform that has all this laboratory equipment attached to it. And all this laboratory equipment is, for all practical purposes, perfect, or is heavy enough to carry out the operations that I claim that I can carry if I write down such quantum states. This is an assumption. This is an assumption here. So what I'm saying is A is something like this, but it also has something of this form, right? So this is my, and then can be in a superposition, but it's the full thing that is like in a superposition, right? Of course, what happens if the reference frames are not of equal size? How I would do such a thing is a very interesting question. And in my opinion, for the moment, is not understood. Although there are some works that deal with quantum reference frame transformations for finite systems. If you look at the latest paper, it's by Anne-Catherine de la Hamet et al. It's called something like perspective neutral transformations for general groups or something like that. It came out last year, I think. It's not on the list, but ask me about it. Okay, what time is it? Let me just compute something very easy and we're finished for this time, for this session. First I will erase then. Where did I put the eraser?
Left in the sink.
Thank you. So let's say we have something slightly different from what we started with in the motivation part, in the classical part. Let's say we have A. We have S. But now, let's put B in a superposition of positions. One here, and another one by dotted lines, I mean another amplitude of the superposition. So this is the situation. This corresponds to the state psi of a sine from A of B, and S is equal, let's say, 1 over square root of 2 alpha of B plus some phase, maybe, if you want. Okay. And now psi of the system, right? So how do we change reference frame? Like that, right? So we want to find this object, which is equal by definition to this. So it's very simple. First, the parity swap means that all these alphas will turn to minus alphas, right? In the first amplitude, I will read out alpha, so I will push this guy by alpha. In the second amplitude, I will read 2 alpha, so I will push this guy by 2 alpha, or actually minus 2 alpha, right? So I will get this. The 1 over square root of 2 comes out, right? And then I will get first minus alpha of whom? Of A. And then tensor product e to the I alpha, because I'm reading alpha, acting on P, acting on psi of S. And then the phase comes out again, is captured here. Then I have minus 2 alpha of A right? This is what I get. What does this mean in pictures? It means that I have something like this, right? It means that now I am Bob, so I'm fixed. And now it is Alice, the one that is fuzzy. With some amplitude, she is at minus alpha. With some other amplitude, she is at minus 2 alpha. But this is not all of it, right? Also the system is translated depending on the amplitude. So with one amplitude, the system is like, say, like this, and with another amplitude is like that, right? So we have an entangled state now. We started with a separable state, of course, of different systems, and we ended up with an entangled state. So this is the first lesson to learn. The notion of entanglement, and more precisely it will be, I will make it more precise later, the notion of subsystem is quantum reference frame dependent. There's actually a very nice paper that was the first paper to point this out very clearly. It's called actually quantum relativity of subsystems. The authors, it's reference, I would recommend you to read this paper. It's reference number 7 in the list. Okay, so we started with a separable state of B and S relative to A, and we ended up with an entangled state of A and S relative to B. There's something strange going on. Let's try to understand it, but first let's go for coffee. What? Questions? question.
So at no point you mentioned the uncertainty on position of the reference frame. So I guess then when you're measuring quantum systems, you have always this problem of uncertainty on the position. Does it come at some point, or because when you write this basis, so yes, when you write the integral on the basis, there's uncertainty then in the.
Yes. So, yeah. I think for this part it makes not so much of a problem. The problem that I was mentioning had more to do with when you put the mass in different locations, and then you want to find out what is the gravitational field sourced by this mass. There's an approximation there that I made in which for each location the particle is very well localized, but yet is not so well localized that its uncertainty in momentum would also contribute significantly to the gravitational field, because otherwise I don't know how to solve that problem, right? It's some sort of semi-classical approximation in which the particle has, quote unquote, a well-defined momentum and a well-defined position as well, and the gravitational field depends to first order approximation only on where it is and not on its momentum fluctuations. To solve the other problem in which you take into account also those fluctuations is harder. And it's an interesting question of whether an extension of these methods could also solve that. But for the moment, I don't know. Yeah.
Is it possible to generate entanglement such that the two particles are entangled in every reference frame?
That's a good question. I think it is. Or to put the question the other way around, how much entanglement can you get rid of by quantum reference frame transformations? There is, I think, a limited amount of it that you can get rid of for a given set of transformations. If you fix that, then I think you cannot make every entangled state separable by means of a transformation. I don't think this is the case. Yeah.
So if I see it correctly, the lower diagram is now seen from B, right?
Yes, this is seen from B.
So then you have a superposition of reference frames of A, like the -2 alpha.
Yes, this is correct. Maybe I didn't draw it very accurately, but yes, this is the idea.
Okay, but so if I now apply again the same transformation back to my original frame,
yes,
basically, will I get another entanglement? Because
no, you will get that.
Exactly this. Okay.
Yeah.
Because in the first one there was no entanglement.
Okay, so
because now the situation is basically the one I had before, but now I have a superposition in A. So I would, expect also that if I now apply a transformation back to the original state, I would suspect an entangled state because I started with basically the same situation.
Right. But imagine from an external point of view, you have like an entangled state between these two. This one observes this one, let's say, but you don't care about that in the beginning. You just say they're entangled between the two being here and the two being here, right? And then you ask the question, how would this see this one? Would it see it in a superposition or would it see it in a normal? And if you arrange things such that the relative distance between the two is always the same, then the claim is that this one will see this one in a pure state, not superposition, not entangled, just separated from its origin by a fixed amount. So this is what's going on, I think. Something very important to note that I maybe didn't emphasize so much, all these transformations are unitaries. They're reversible and they're unitaries. Yeah. Good. Any questions?
When you write psi vs in the first dot, right?
Right.
Alpha b plus e power I alpha.
This one.
So you observe the superposition from the point of view of A, right?
Yes. Yes, this is the idea. Yes.
Because then you say that after applying that transformation, you end up with an entangled state.
From the point of view of B.
And for that, the superposition there is quite important.
Exactly. Yes, this is a very good point. Yes. Yes, this thing, in some sense, translates superposition into entanglement, if you wish. Yeah.
So now the question is, right, if you're defining this as a quantum reference frame, definition of a quantum reference frame, or transformation, basically.
Yes.
How do I get that one? Because...
How do you get which one, sorry?
For example, you told that quantum entanglement is basically a quantum reference frame originated notion. If you interpret it that way, then what about the superposition there?
I'm not sure I understand the question, but let's say I start with this state and then I apply the inverse of that one, then I will obtain this one. And I would obtain superposition, coherence. Is this the question?
I will maybe in the coffee break.
Okay, good. Let's make a break then.